I also need my computer to tell me what to write on my pieces of paper, because that's my relationship with technology. Right. Where was it hiding? It was here. Zoom in. Right.
Okay, ready to go?
I hope so. Let's see. Right. I want the rules. This is where we got to zoom out a bit.
Okay. Okay, everyone. Welcome back after lunch. So we'll have our second lecture on type theory by Conor McBride.
All right. So just as a reminder, we distinguished these notions of the person who sends you a term or a type or whatever it happens to be, and the person who makes a promise about it. I mean, maybe it's not people, maybe it's the, computers. But we're operating on the basis that whoever is asking, does big T accept little t, is promising you that big T is a type. Whereas when you ask someone to check, does big T accept little t, you're not making any promises about little t. I mean, that's why you're asking the question in the first place. You're hoping the person that you're asking is going to make you a promise about little t. In particular, you're hoping they're going to say yes to your question. Likewise here, when you pose the question, please synthesize a type for E, you're hoping that the person you're asking is going to say, yes, E's okay, and S is its type, and they're promising you that the type is okay. So that's how we distinguish what it is to be a citizen. A citizen is a signal whose sender is also its guarantor, whereas a subject is a signal where the sender makes no promises about it and is hoping the receiver will make a promise about it. And that's how the interaction here works. I also, if you remember, said that we have a kind of flow of information, that we have explicit binding sites for the pattern variables. So information kind of flows clockwise round a typing rule in time, from the inputs and subjects of the conclusion, then round through the premises, where now it's the outputs from the premises that give us new information that we can pattern match on, and then eventually round to the output of the conclusion if it has one. So you can think of time as going clockwise, which is quite an appropriate thing for time to do. So these, I wrote these rules down. I didn't write down the reduction rules. So let me just quickly do that. Once again, radicals which are embedded are basically things which are no longer computing, so they no longer need a type annotation. And we also have lambda xt in pi x in s t applied to s computes. This time, both little t and big T need to be substituted by radicalized little s. And this is a much more exciting situation, because although big T is a component of this whole pi type. We're doing a substitution to it. So the type is not in any syntactic sense necessarily getting smaller. So we aren't getting an explanation of normalization just for free out of this T being a component of this pi type. And indeed, we know that this system is not normalizing. So if you want to play this game, you need to do, if you want to make this normalizing, you need to do something to stratify your universe layers so that you can turn a type into a large enough ordinal that this does turn into an inductive explanation. So basically, you need this T to be bigger than all the things you can instantiate it with in order for this to be some sort of reduction in the weirdness of the types. Okay, so I want to move on to proving some stuff about this system. In particular, I want to prove a type preservation result. But actually, you can see that's going to be a barrel of laughs, right? If you, maybe I can find my simple types, right? Right. In simply typed lambda calculus, when the terms compute, the types stay still. I mean, they don't, you might chop them up into smaller types, but no computation happens inside the types when some computation happens inside the terms. The terms are so we can basically form a type preservation claim which says if tau accepts t and t takes a step, then tau will still accept what t becomes. And if we can synthesize sigma for e and e takes a step, we'll be able still to synthesize sigma for whatever e has computed to. Life is rather more awkward here. Because you know, what happens if little s takes a step in this rule, that might well show up in what the type does. So we're going to have to think about what happens when we're going to have to allow for some sort of play in how the citizens compute whenever the subject does. But that's not at all obvious. But one thing we do have at our disposal is the property that the schematic variables which occur in the conclusion subject are used linearly in the premises. So that's to say this F and this S play the role, so the only subjects in the premises, the subject F and the subject S in these two premises are coming from the subject of the conclusion. And that tells us that there is some hope for doing an induction on derivations that might just work. We're going to say, what happens if the subject does a bit of computation? And in our induction hypothesis, the bits and pieces of the subject will be allowed to do some computation, whatever subjects are allowed to do. There'll be an induction hypothesis that says those subjects might have done it. what computation we allow citizens to do is rather independent of that. Citizens, well, for one thing, we trust citizens. But for another thing, we can see we're going to have to let the citizens do at least as much computation as the subjects, because this type here, this output, needs to be able to compute at least as much as little s does. So that's told us a few things. Well, first of all, that we're interested in what computation happens in the various pieces of the subject. So that suggests to me that we stop thinking about single steps of computation and do something that's slightly more liberal. Okay, because if we know that f of s takes a single step, then either f takes a step or s takes a step, but not both. So we could consider 0 or 1 steps, because if f of s takes 0 or 1 steps, then f takes 0 or 1 step, s takes 0 or 1 step. That's kind of not, it's good that we're going that way, taking 0 or 1 apart. We get a sensible induction hypothesis. But it's somehow, I don't know, it's ugly. There's some connection between how the two induction hypotheses might get used. So the nice way to do it is to formulate parallel reduction. Yeah.
Oh, thank you. I'm a little confused behind. So I see no rules for like an evaluation context. So what is telling us that either f or s can reduce?
Okay.
What allows that?
Okay. So what allows that is the rules I haven't written down, which say that forward computation is contextually closed. Forward computation is the contextual closure of the single step. So I've just written down the contraction rules that do the actual work. And then I'm basically saying, you can do those anywhere. Okay. So in fact, the reason why I haven't written those rules down is that I don't actually I want to do something different. So, but there's lots of hands.
When you say, so when you say you can do computation anywhere, can you also do it inside of lambdas?
Sure.
Okay.
Okay, so how about instead of you asking me what are the rules that I haven't written down, I write them down. Deal? Okay, so what I'm going to do is, so starting from these contraction schemes, I'm going to show you how to generate a notion of parallel reduction. So the key idea of parallel reduction is that, like, when you look at a term, it might have more than one place you could take a contraction step inside it. So you've got a bunch of choices of steps you could take. There's no fixed evaluation order. So parallel reduction asks the question, what if we were allowed to choose freely from the set of redexes we can see? So that's to say, I can see a beta redex here. I can see this, I call an upsilon redex. I can see one of those somewhere else. That gives me a choice of things I could do. And what if I were allowed to do none, some, or all of them? So let me show how that goes. So first of all, you the symbol we use is a triangle. I have to do it for both syntactic categories. So step one, absolutely everything. These relations are closed under all constructions. So in particular, we will have that a variable reduces to, I should do that over here, a variable reduces to itself. If f reduces to f prime and s reduces to s prime, then fs reduces to f prime s prime. Lambda x dot t reduces to lambda x dot t prime if t reduces to t prime given some x. So I'm just recording that x is in scope here. Right. And you can fill in the rest of the, but is it fine to see, can you see what this is going to be for all the syntactic constructions? So I'm basically saying, if the substructures compute, the whole thing computes. So this is going to give us, this is going to be our contextual closure for everything. But then I have to say what happens with the redexes. So I'm going to say that radicalized, I should be doing this on the right. Let's do it. No, it belongs here. I'm being daft. This is the bit I've less well practiced on. This thing will compute to t prime. Oh, sorry, triangle. If t computes to t prime. And then what happens for beta, let's see if I can get this correct. Lambda x dot t in pi x in s t applied to s computes to t prime in big T prime instantiated with little s prime in big S prime, provided x says t becomes t prime, s becomes s prime, x says big T becomes big T prime, and little s becomes little s prime. So that's to say you're allowed to do a bit of computation inside the components of the redex and then contract the whole redex itself.
For the radicalized case, are you not allowed to step the type?
Well, you're allowed to step the type and then throw it away.
Okay.
I mean, there will be a structural rule for radicals as well, which will say t in t computes to t prime in t prime if t computes to t prime and big T computes to big T prime. So yes, I should probably have added, it's harmless to add that the type can step before it disappears. So uniformly, I mean, I hope you can see the recipe for turning a contraction scheme into a parallel reduction rule. You just say, let all the schematic variables take a step and use the stepped versions in the reduct. When?
I think that has just reduced count further reduced.
That's correct. It's parallel reduction. What's parallel about it is that all of the redexes you can see can be reduced, but none of the redexes that are only generated by the first after one step are available yet. Okay. So one thing we notice, because of all of the structural rules, parallel reduction is reflexive. What's more, it is clear, I hope, that single step reduction is included in parallel reduction, because you could simply choose to do that one and none of the others. Okay? So it's immediately possible to formulate the system, to reformulate the system in terms of parallel reduction instead of single step reduction, and we lose nothing. Okay, so the plan is that the computation we're going to let the subjects of our judgments do in our type preservation statement is parallel reduction, and our linearity setup, the linearity in terms of when things are used as subjects of premises mean that if the subject conclusion takes a parallel reduction step, that means the subject premises have only taken a parallel reduction step. So we're hoping that if we're doing a proof by induction on derivations, that our induction hypotheses might stand a chance in hell.
Yeah, I have two questions. Like, first one is just basic. Do you have like separate syntactic sorts for terms and types?
No.
So the reason why it is done that way, because you don't have to define separate judgments. Is that the reason? Like otherwise you have to if it's separate syntactic sorts, then like the in and ni should be defined separately for two things, right? In order for the
I mean, one could in some situations say that there's a separate notion of what it is to be a type from what it is to be a term. Yeah. And then you would need type formation judgment as well as ni and in. Then you might distinguish kind of what it is to be semantically a type from what it is to be syntactically the name of a type in some universe. So that's to say, there might you might think there might be a type of data descriptions and some operator that turns a data description. I mean, the data description is being some piece of data itself, and something that an operator that explicitly pastes the term language, that explicitly embeds the term language into the type language. Here, I'm not doing that. They all live together. Does that make any sense? I'm trying not to talk too much about a type theory that I'm not presenting.
Oh.
But it is sometimes done that way.
Yeah, so one more question, like I might have, so you might have already told that, but I missed that, like, what do you mean by reducing only those reductions that you can see? Like, I don't.
Right, if I write a big term, it might have multiple.
So you're going to say that like some might be meta variables and some that, like if you take a term, some of it could be meta variables and some could be like that actual reductions.
Right. So I might have a type which looks like, I don't know, pi x lives in, and then here I'm going to write lambda x dot x radicalized at pi x in type. So that's radicalized thing. I can apply that to type, and then I have to embed that, and then I will make down here another copy of the same thing. I'll alpha convert it for no good reason, just to make it look a little bit different. Right, so that's a valid type. It so happens that in both the, so it's obfuscated in both the domain and the codomain. I've deliberately put a beta redex. So in a single step computation, I would have to choose one or other. In parallel reduction, I'm allowed to say, I can see two beta redexes. Let's do none of them. Let's do the first one. Let's do the second one. Let's do both. Right. Now, only after I've done that beta redex, so this thing here will compute to star colon star embedded and typed at star and embedded. So the beta redex has made two epsilon redexes appear, which were not in the original term. I have to save them to my next parallel reduction step. I can't do the betas and the epsilons in one parallel reduction step because the beta redexes, the epsilon redexes were only revealed by doing the beta. So the ones you're allowed to choose from are the ones which are already present, not the ones which become consequently present. That making sense? And it's got this sort of pleasing property that it's kind of structurally closed under all term forming operations. Okay. So I'm figuring out what I want to say. Switch to exciting shade of purple. Okay, so right, the rules don't talk about contexts, but the theorems that talk about judgments need to talk about contexts. So contexts you should think of as inputs invisible in the rules. Right, so the question is, if I have a judgment, here are our two judgment forms, now with contexts that might compute. Right, so what I've said is somebody might step the subject with a parallel reduction step that now points downwards. Okay, now the question is, how can we formulate some property of T prime that somehow still holds? We're interested in what on earth, under what circumstances we can get back some judgment about T prime, and likewise E prime. What do we notice? Here's a rule, for example. So we have to just look at the rules and see how much trouble we're in. Here's a rule where something that comes in the subject, so it might be this thing's allowed to step. Right? But you can see this S ends up in the context. So if my induction hypothesis doesn't let the context compute, I'm in trouble. Okay, so that tells us something. The context needs to be allowed to compute at least as much as the terms are. And where else does stuff happen? Well, it's certainly the case that things which started up in terms end up in types. So we're in the same situation. The induction hypothesis had better let the types compute as well. So we might hope to be able to show something. Well, okay, like that. I'm gonna show you a trick, which I hope Chris will appreciate. So there's some quantifier alternation going on here. I can say in words, if you know, gamma says big T accepts little t, and they all take a parallel reduction step, it's still true, right? So what I'm saying is that the devil provides gamma big T little t, gamma prime T big T prime little t prime, and the reduction steps that relate them. And my job is to just show that the judgment holds. So in the interaction with the devil goes at time 0, and I have to respond at time 1. So yeah, so an interaction, these sorts of interactions with the devil are these sort of quantifier alternations. The devil gets the universal quantifiers, and you get the existential quantifiers. And the devil goes first, so the devil goes on the even stages, including stage 0. And you get to go on the odd stages, right? And the minimal annotation that works, that tells the quantifier story, is to label with a number anything which arrives after its boundary. So here I'm saying that it's not, although all of these things exist at time 1, the fact that time 0, the fact that this judgment holds on the judgment on the bottom holds of gamma prime, big T prime, and little t prime is something that I pay up at time 1. So that's nice use of color, but you were always having to say which color, what order the colors happened in. So this is a nice little trick that some of us here cooked up. Okay, so this isn't true, by the way, but it's nearly true. Okay, I'm trying to remember why it fails, but it's quite fun. Right, this is a tricky one though. Right, so same deal applies. We have to let the context step. The trouble is, if the context steps, let's suppose little e is a variable, little x. Suppose this is x. And suppose in the context, there's some hypothetical judgment that says x lives in S. And that's how I made this judgment hold. If the devil decides to step to step big S to S prime, I can't give back the old S that came in. The devil has done a compute step and I'm in trouble. I can't restore the old judgment because I'm not allowed to go backwards. The rules only let me compute forwards. So I have to have the freedom to respond to the devil's computation with some computation of my own. So here, but it's the S prime that I label with the 1 to say that And that says that at phase one, this gets delivered by me, and so does that. So I get that whole region arrives at phase one by labeling one of the things that shows up there. So that is to say, when I'm synthesizing a type, the devil can step the context, the devil can step the subject, and in response, I can step the conclusion, the output, to cope with whatever the devil's done to me. Okay, so I'm not going to shove it into a puddle, but it turns out that this is not quite strong enough. It turns out, I forget in which cases, that allowing that there are too many things going on, and only allowing the context and the type to take a parallel reduction step is not strong enough. So the fix is to allow citizens to compute as much as they damn well please. Okay, so that's a subtle one. So what we're saying is the things that we trust are allowed to compute arbitrarily. The things that we don't yet trust are allowed a parallel reduction step. And the devil is allowed to compute the inputs, and we are allowed to compute the outputs.
Second case is the context not allowed to step multiple times.
Oh, yes, it is. Sorry, that's just my, and the devil's allowed to do it. Okay, so that's the deal. If the devil makes the inputs compute, and I make the output compute. So here you can see that if the devil steps the type of little x in the context, I will do exactly the same step in the conclusion. So the devil doesn't get me into trouble here by computing the context. Okay, how are we doing for time? I'm about halfway. So this took me ages, and you can understand perhaps. Well, yeah. So in general, this is delicate stuff, and it was absolute misery trying to do this stuff. It was about 2015. I was working on this for the forerunner of quantitative type theory, and my inductions would just not go through. Partly, I was making the traditional type theorist's mistake of writing typing rules down that did revalidation of citizens, right? If something that is in a if something which is in a citizen position in a rules conclusion ends up in a subject position in a premise, my induction hypothesis won't cover it. Right? So this was the deal that I found. I found I needed the citizens to do more computation than a single step of parallel reduction. I can't remember exactly which which rule in the proof required that? So, so that was the deal. I needed the citizens to do arbitrary computation. And correspondingly, the proof broke if anything in a citizen position in the conclusion ever ended up in a subject premise, subject position in the premise, because the subjects were only allowed to do a single step of parallel reduction. So prove that this was where strict subject premise linearity came in. No rechecking citizens. Citizens can do arbitrary computation and must not be rechecked, because otherwise there's no chance of proving anything straightforwardly by induction on derivations here. Okay, so that's where we got to. There's something else we're going to need. Let's look at a few things. Right. Consider this rule. Right. The judgment that holds is T, I'm going to need numbers here. T naught checks T. Okay, so that's what used to hold, and it was derived by T naught takes a single step to T1 and T1 checks T. The only trouble is that the devil has decided to send T naught to T2 and T to T prime. What the hell am I going to do? How do I make use of my induction hypothesis? So it's fine. I've got T making a parallel reduction step to T prime. I'm allowed to do any computation I like from T1. But I need to draw a conclusion that concerns T2. How am I going to fix it? Confluence. I need some T3. So I need some T2, some T3 that I can get to by arbitrary computation from both T1 and T2. And then I can use this rule multiple times for every step that I need to put in to fix up. So for every step in this reduction sequence, I need to deploy this rule. So one instance of this rule will turn into a bunch of them.
So I guess given that you can apply this rule any number of times that you want, is there any purpose to keeping the two reduction relations separate still?
Not really.
Okay.
So I was just, because I formulated this rule in terms of single step, I just wanted to emphasize that we could recover by using this rule once for each single step in this reduction sequence. We can get back to a derivation of T2 accepts T prime, but confluence is vital. Right, so that's the point, is that anytime your old derivation used computation in one direction, the devil can use computation to push you in another direction. And you need to be able to get back to a common point. So we're going to need that reduction is confluent. But then we've just checked this single step computation rule. We should look at the other one. Okay. So now what happens here? My old derivation was E lives in S, and E took a single step to E prime. I invoke, sorry, yeah, this was, the old derivation was, sorry, this should be, let me copy the rules sensibly. I'm going to call this S1. This is E is in S0, and S0 steps to S1. Okay, so this time when I invoke my induction hypothesis for E stepping to E prime, the devil tells me that E prime is in S2, which is computed arbitrarily from S0 and is not necessarily that much, you know, the devil doesn't have to choose this step. The devil can choose any computation available in S0. Whereas I have to show that I can recover some downstream, some type that's computationally downstream from S1. But I've got an induction hypothesis that tells me about S2. So what am I going to do? Same trick. I'm going to produce a common reduct S3 from both S1 and S2, and I'm going to use my freedom to compute arbitrarily to compute S3 as the type in the derived judgment. So that's where I need to be free to compute arbitrarily in the output. Yes. Sorry, yes. Okay, so confluence is going to get us out of this jam a lot. Okay, so I don't want to do this proof in detail because, well, maybe we should actually. Okay, so let's, but we can kind of work our way around to see how things flow. Because what it boils down to is that that confluence gets us out of all the trouble we're in, and the way that the formulation, this formulation basically says that you're always free to match the computation that the devil does. So this is your freedom. This is the devil's freedom. Okay, so let's look at this rule, for example. Well, the devil can't step the type. They can step the context, but we can do the same context step in the induction hypothesis when we're appealing to induction. Yes.
Maybe one question that was a little bit earlier, but maybe you're getting to it, but I'm a little bit confused. So I see that this is some kind of communication, and you can say, okay, it's communication and therefore some kind of alternating proof of two players, fine.
Yeah.
But I don't see how you state the induction principle regarding to this alternation, because I'm used to normal typing rules, and for me, I can't match the alternating part to the induction hypothesis at this point.
Okay, maybe I should write the statements of these rules of the theorems more clearly. So this is for all gamma prime t prime little t prime, if gamma says big T accepts little t, and gamma computes arbitrarily to gamma prime, and big T computes arbitrarily to big T prime, and little t steps to little t prime, then gamma prime says big T prime accepts little t prime. Whereas the other one says for all gamma prime, E prime, and S, if gamma says E is in S, and gamma computes arbitrarily to gamma prime, and E parallel reduction steps to E prime, then there exists an S prime such that S prime can be computed from S, and gamma prime says E prime is in S prime. So the deal is the devil can do arbitrary, so the devil is providing the inputs. Yes?
Thanks for this. So
Yes.
I could move the gammas, primes, and the p primes. Thanks.
Yeah.
Sorry, this is a bit of a nitpicky question about the computation rule for synthesizable terms that you use to motivate confluence. Because your gamma primes, t primes, and t primes here are to the left of the assumption of the derivation rule, you have to do that trick.
Yeah.
But if you move them to the right, you wouldn't. You see? So I can assume
No, I
after
don't.
you could put two for alls.
Uh-huh.
One before the says assumption, and one after in the top line. The second one.
Yeah, so it's certainly the case that.
So you would strengthen your induction hypothesis, so you wouldn't have to rely on the devil giving you exactly the right. I can take it offline.
Yeah, I mean.
You still need confluence, just not for the.
Yeah, I mean,
reason. Yeah.
so yes, I am going to transform this goal so it looks like for all gamma t, if gamma says big T accepts little t, then I'm going to permute this to the front before I do induction. That's for sure. So I want the most general induction hypothesis I can have. So I'm going to pull the thing. So I'm going to keep as many things universally quantified in the induction predicate as I possibly can. And I'm terribly sorry that I didn't say to do that, because for the last 20-something years, my induction tactic has been doing that for me. So I just, assume that whatever is deploying an induction principle is going to give me a maximally general induction hypothesis. So that means pull the thing you're doing induction onto the front and keep as many things universally quantified inside the induction predicate as possible. So you're free to choose when you're looking at your induction hypothesis for each premise, you're free to choose the things you compute to. But under those circumstances, the devil is free to choose. So that was the situation here. I was free to choose to deploy the induction hypothesis relating E to E prime. But the existential quantifier in the induction hypothesis belongs to the devil. So the devil pushed me to S2, where I didn't want to go, because I wanted to go to S1. So I have to use confluence to cooperate with the devil in that situation.
Thanks.
Right. So, okay. Let's look at the pi case again. So the devil gets to do small steps for S and T, and I go, well, that's fine, right? In the context in the premise belongs to me. So I can mimic the devil's step here. And my induction hypothesis is good for this little t. Little t here will only do a parallel reduction step. So that's fine. Okay, let's do a nasty rule. Well, let's have functions. Okay, so the devil computes this type arbitrarily. Now, note that no amount of forward computation can stop a function type being a function type. So, good, I will still be able to make my new derivation using this rule. Likewise, no amount of forward computation can make a solitary lambda stop being a solitary lambda. Then what happens? So the devil has done some computation on S, and I'm free to do the same computation in the context when I'm invoking the induction hypothesis. The devil has some computation on T, but I'm allowed to do the same computation when choosing the type that I use in the induction hypothesis. And little t has done a parallel reduction step, and I'm allowed to make little t in the induction hypothesis do a parallel reduction step. So I win, right? So basically, the devil sometimes has to can choose arbitrary computation, but only in things which match canonical patterns, things that can't be destroyed by computation. So they'll match the same patterns. So whenever I choose, when I choose the expressions that I'm going to pick, I can do the same computation. Okay, let's have a look at application. So here, we've got an application. The devil is allowed to step little f and little s. In my induction, when I'm deploying the induction hypothesis for this premise, I can make the same step to little f. The devil can do whatever the devil wants to this pi type. Fortunately, no matter what the devil wants to do, it will still be a pi type. So I can harvest the pieces. The devil will compute big S and big T any way they like. But I can do the same computation when I'm choosing the type here. Right, so note, it's the same pattern expression situations. The devil can do arbitrary computations to things that are matched by patterns, and I can always do this, so that for the things at the binding sites, I get to choose the things at the use sites, and I can always mimic the same computation. I can always use confluence to get me out of any conflict between the computation the devil decides to do and the computation that I wanted to do. We can both be right. So the message here is that, this induction, just by using confluence to compute our way out of trouble, is actually going to go through. And I don't think that's a coincidence.
So you're saying we need to use confluence. Are there any nasty hidden things in proving confluence?
I was going to do that next.
Okay.
Okay,
So some type theories don't have confluence. The places where you use it, maybe places where you wouldn't needs, you know, it wouldn't break when you move to more.
Okay, so good question. And slightly subtle answer. I'm going to arrange by hook or by crook for beta reduction to be confluent. I know that's quite an ask. But there's going to be a whole other notion of equality. I mean, the high level picture is when something has computed enough to match a canonical type former, that has to be non-destructible. And whatever computation the devil can do to the things that match the patterns, I have to ensure that those patterns will still match, and I have to be able to mimic that computation. I'm presenting a system where I'm using a particularly syntactic formulation of computation steps. In real life, I'm much more interested in systems which admit much more interesting notions of normalization, which still mean there's going to be some kind of canonical representative of the equivalence class. So yeah, if we're moving to a situation where kind of just thinking naively about rewriting isn't going to cut it, then there are bigger guns. Likewise, though, it's noticeable that if you're in a situation where, so the one thing I am saying is that what you need to be confluent is enough computation to expose canonical constructors for purposes of pattern matching. You don't have to put all the computation into evaluation. Like, see what I'm saying? We only use these things to try and put types into a form that will match pi. Yeah, the reduction relation only has to do enough work to reveal a pi type if there is one. That's what we use it for. If we want to do something cleverer with the equational theory of these things, we have a look at this relation instead. Right, so at the moment, I'm getting away with saying I'm only doing beta. So this is, once again, exact syntactic equivalence up to alpha conversion, which in my case is always, because I always implement this, choosing canonical representatives of alpha equivalence classes. It's exact syntactic equality. But yes, if I wanted to do something like allow eta laws for functions, so to make f the same thing as lambda x fx, I don't do that here. I don't do that in the reduction behavior. I do that in the equality test. And likewise, there are all sorts of additional bits of algebra that you can safely punt to the equality test, because that reasoning isn't necessary to reveal that a pi type is a pi type. Right. How am I doing? I'm supposed to stop in 20 minutes. Okay, so let's okay, one thing I didn't do, actually, I should do one step of this which actually involves which actually involves stepping. Right. Okay. So once upon a time, this thing had type it had type big T of little s in big S. That was the type we synthesized for it. That's the left-hand side. Okay, so what happens, taking this apart, this must have been type checked with the application rule. Well, actually, it might have been type checked with this rule also. But at some point, there must have been an actual application that, so yeah, where this was type checked. So in full generality, we might have a situation where this is some T prime, S prime, S prime here. But that's fine. Because what's going to happen, we invoke our induction hypothesis for this this function, which is a radical. So the devil is free to compute yet another version of this function type. So my induction hypothesis will give me that that thing lives in pi x in S double prime, T double prime. But you know what I'm going to say. You know, I don't care because I can confluence my way out of this problem. Yeah, so I don't know, it's difficult to do this sort of thing without fighting a computer. But yeah, the yeah, this will take a step, but it'll only take steps inside little t, big S, big T, little s. So I can, of course, replicate. Oh yeah, one thing that is lovely about parallel reduction, and this is actually the real reason for using parallel reduction in the formulation of this statement, is that parallel reduction is stable under substitution. I told you, this is stable under substitution club. And yeah, so use, you know, single step reduction isn't stable under substitution, because if redex gets copied, you have to, it takes you lots of steps, one for each of the copies. Whereas parallel reduction, you can see all of the copies at once, so you can do them all at once. So yeah, so stable under substitution, stability under substitution is crucial, because that's what lets us do a parallel reduction step to this whole thing, because we can do parallel reduction steps for each of the 4 pieces, and we have parallel reduction being stable under substitution. So that allows us to step the conclusion. And once again, we're going to be pushed in several different computational directions, but we're going to just take a common redux for everything, and we're free to choose the type that we give back for this thing. So although everything computes forwards a bit, we can react by taking common redux and computing even more, satisfying all the demands. Okay, so the message here is that the demands of, you know, who gets to choose which computation happens is in alignment with the inputs and the outputs. So because we had a flow from binding sites of pattern variables, of binding sets of schematic variables in patterns to use sites of schematic variables in expressions. And because we have aligned who allows, who chooses which things compute with that distinction, all of the structural cases of type preservation go through without any difficulty whatsoever. Indeed, I conjecture that there's a general theorem about type systems that you can formulate by rules systems that obey the discipline I've been describing, which is that type preservation is reducible to the type correctness of the individual contraction schemes. So that's where all the work is, because we've been sufficiently disciplined about the information flow through the typing rules that those, provided that our system's confluent, that we just can't, there's no trouble the devil can push us into that we can't confluence our way out of. Okay, so why is this system confluent? Well, here I am going to return to an entirely traditional way of doing things. Where are my, I hid my contraction schemes from myself. I'm good at doing that. Where did I put them? Here they are. Okay. So confluence is going to follow from the fact that if I have some term T naught and it can take a parallel reduction step to T1 and a parallel reduction step to T2, then I will be able to get them back together with a single parallel reduction step each. Okay, so this is absolutely, now I haven't proven this yet, but this is the plan. So it's to say parallel reduction has the diamond property. So how does the proof go? We observe that the single step reduction relation is included in the parallel reduction relation. Sorry, that should be a subset, which is further included in the iterated single step reduction relation. So if someone gives me a whole load of steps from T0 to T1, so this is an iterated, so a whole bunch of why am I just stop making a mess of it. So somebody gives me a bunch of reduction steps to T1 and a different bunch of reduction steps to T2. I can deduce that I could have taken a bunch of parallel reduction steps instead. But what is this? So yeah, and then I can construct. So someone's given me, so this is a whole bunch of these steps. This is another bunch of these steps. Okay, so what do? I use the diamond property to tear a strip. like that. And then I'm ready to use the diamond property again to tear another strip. And I keep going until I've constructed the whole parallelogram. So if I've got so this is what I needed. If I've got a particular formulation of computation which includes single-step reduction and is included in multi-step reduction, and moreover has the diamond property, then I'm home. Yeah.
So taking a step back just for a second, could you show the other paper, which you just showed with the inclusions? Yes, this one, thank you. How is it that the parallel reduction, the triangle,
Yeah.
is included in multiple single step reductions? Because what if you compute something inside of a lambda in one step, then how do you recover that through multiple single steps?
Let's check. Right. So it's going to, a short parallel reduction step can turn into quite a lot of work for single steps. But let's actually, where did I write down the key rule, which was the beta rule? Yeah. So here is a parallel reduction step where there's a lot of work going on, because before I do this beta redex, I've got all of these other bits and pieces. Okay, so by induction hypothesis, I can turn each of these 4 parallel reduction steps into single step sequences. Okay, single step reduction is contextually closed, so I can take my t steps to t prime single step and turn it into left hand side with t steps to left hand side with t prime. My induction hypothesis will at least let me replace the t by the t prime. Okay, now I do the same thing, contextually closing to turn S into S prime. Then I stitch onto that the reduction sequence, which steps big T to big T prime. And then I stitch onto that the reduction sequence that steps little s to little s prime. And then I take one more step, in the beta step itself. So I'm going to use my induction hypotheses and concatenate, and plus contextual closure, and concatenate everything together to make one big long sequential reduction sequence. Right. So the high level message is how do you turn a parallel reduction step into a single reduction sequence, is by doing things one at a time.
Yes,
Right,
yes.
yes.
So I think I'm just a little bit more confused about how when it's embedded in something. So on like the top left rule, right? So if you have a lambda x dot t, and you can take this, you can compute the t to a t prime.
Yeah.
And it remains in the lambda.
Yeah.
But I don't see the rules in how you can do that with the single step, because you're going to.
Because I didn't write them down.
Oh,
I didn't
okay.
write, so the contraction schemes turn into reduction steps by you can contract in an arbitrary one whole context.
Okay.
So so these things you have to recontextualize so that you can concatenate them together.
Got you. Okay.
Right.
Thank you.
Okay, sorry about that. I didn't write those rules down earlier because I wanted to write these rules down instead. Okay, so where did I put the contraction schemes. But anyway, what's the key point is that there are rules which we had that rule and we had blah radicalized at capital blah thingy computes to something. Okay, doesn't really matter what's going on. The question is, right, and we noticed, maybe I should find it. Actually, this will do. You'll notice that all the schematic variables in this rule stand for things that live in the checkable fragment. And there's a good reason for that. Because things that live in the synthesizable fragment can compute away. So what that means is the thing that screws up the diamond property for parallel reduction is if choosing one redex comes at the cost of destroying another one. And by construction, that can't happen here. What do we have? So there's always something canonical here, something canonical here. The only way, right, this thing, a beta redex lives in the synthesizable fragment. So the only way another beta redex could show up inside this one is if it's inside an embedding of some term that is matched inside. So it's going to be inside something matched to one of these pattern variables, and it's going to get copied intact. So that's right. The crucial thing is that contracting this beta redex can't tear apart any other beta redex. Moreover, it can't stop. Right. You notice crucially, there's no sign of an embedding mark in any of these rules on the left hand side in the pattern, which means that anything which looks like this or anything which looks like this has to stay intact and get copied into the right hand side of the rule where we can still hit it. And likewise, anything which looks like this that lives inside a radical has to be inside either the little t or the big T. So again, it's either going to get thrown away or copied intact. So that's the key thing for confluence is that kind of orthogonality property, where if you've got overlapping redexes, they have to overlap sufficiently deeply that contracting the outer one does not destroy the inner one. Right. So that's cool. So by construction, the bidirectional setup imposes confluence on you. In fact, there's a lovely thing about patterns if you cook them correctly. So patterns only address the kind of canonical form, the canonical parts of terms. So those which are fully evaluated. So you can match against stuff that isn't going to get destroyed by computation. Okay. If you throw into your language of patterns what I call the grumpy pattern, if you ask, does the grumpy pattern match? Does some term match the grumpy pattern? The grumpy pattern says no. Then is delightfully true that for every pair of patterns, there's a unique pattern such that both of your separate patterns match if and only if the combined pattern matches. Handy little universal property in the category of patterns and pattern refinement. You know, so that basically means that what you do is you unify the type patterns between the introduction rules and the elimination rules. So here, when does this type match one of these types? Actually, straightforwardly, that's what tells you can construct a beta redex. So you look at all your introduction rules, you look at all the elimination rules, you pairwise unify the types, and that tells you which beta redexes are possible. And then you have to say what they contract to, what they reduce to. But what I'm saying is at a high level, the fact that you can do pattern unification, so unification of patterns, there's a separate thing called pattern unification, which is not what I'm talking about. The fact that you can combine two more general patterns into a more specific one is what gives you confluence by construction, which is what in turn gives you a super easy time proving type preservation. I'm sorry that was a bit more scatty than this morning, but there we are, we got there. Okay.
Time for coffee again.